the phone. You should say that she can hear someone that is not muted, but he must be you. Hello, everybody. Good afternoon. Welcome to the Geotalks today, and we have our guest from the industry that is nice to have in our School of Geosciences. Today is David Lekgenge. Lekgenge, thank you. Donald Lekgenge. Thank you. Sorry, I messed up completely the name. And Donald Lekgenge is graduate in geology from the Free State University, and at the moment is busy with his master in the School of Mining Engineering. He's actually an entrepreneur. He has many ideas into geosciences and especially mining. And today is representing ThreeDify because he's very passionate about data capturing and transforming all of this data that you collect into the field in something that is manageable and eventually meaningful for the down the line in the mine value chain. Thank you so much, Donna. This is for you.
Good. Right. Thank you again for the invitation. Special thanks to the School of Mining, Wits School of Mining, of Geoscience, for the invitation. And also again, thanks Dr. Linda for the invite. I think the very first conversation I had with Dr. Linda, she was so passionate about. She spoke highly about her students. And I could see the passion and the dedication and love that came through as we were having a conversation about the students. So thank you for that. So as Dr. has introduced me, my name is Donald Lekgenge. I'm a mining professional with a geology background. And today my geo talk will be focused on the value of having a all-in-one platform. So, but because my audience are mostly geologists and future geologists, I'll spend a lot, most of my time will talk on the first part, which is in resource evaluation, and then just touch a bit on the reserve optimization, mine planning, and hopefully I'll get to the simulations as well. All right. So to introduce myself again, or the company that I represent, I work for a company called ThreeDify. It's a Canadian-based company, software company. They're based in Ottawa in Canada, and the company is dedicated to developing high-performance software solutions to unlock the economic potential for our clients when we're working on projects. And our mission is to empower our clients to turn their data into insights, response to project quickly, and improve efficiency and profitability and sustainability. And obviously, when you have this in line, you can be able to shorten your decision making, and that also at the end of the day that turns into money in the mining industry. And lastly, the software, which is GeoMine, it's based on company and the software that are based on a deep mining domain knowledge combined with advanced mathematical optimization and 3D computer graphics. And I think the last part there you'll be able to see when I go into the demonstration, because the presentation, it won't just only be PowerPoint presentation, but I'll also try to move into the software side of things, just to show how geologists would just take raw data, make sense of the data, and just to paint a complete picture, and the picture be handed over as Dr. mentioned to the downstream processes where the mine design or the method of mining can be decided, and yeah, we'll just take it from there. So I'm just going to spend a bit of time on the presentation, on the PowerPoint presentation, and then jump over to the software side of it. All right. Believe me or not, this is me 9 years ago, 10 years ago, at a gold mine in the Northwest. I can't really tell what I specifically focusing on, but I know for a fact that I was mapping a development tunnel, and I was probably looking for the reef, right? Because usually this happens when the mining department would all of a sudden, reef would just disappear, and they would just call in a geologist just to come and tell them if the reef went up or down. And I was probably just looking for the reef, and I think the picture just represents a lot to me, because this picture just it's more like how people in the industry or in mining sees geologists. People just come and find where the reef is and just tell them if the reef is up or down due to geological structures, right? But there's actually more to us, or there's actually more to the science of geology, and I'm gonna try to sort of like break it down to you guys on the software side of things. So we actually do more than just to tell the mining guys that the reef is up or down. Okay. So the value platform, right? So this is the value of having a platform. So mostly what happens in the mining industry, you'll find that most of these softwares are siloed based, so they're not connected. They don't talk to each other, right? And this can lead to a lot of it can lead to data not being how can I put it? Not working well with each other. Sometimes we might have like one version, 20 million version of one thing, and that can lead to a lot of mistakes when it comes to your ore bodies, or later on creating your 3D block model, right? So the advantage of having a platform is you are able to amalgamate all your data, or amalgamate or connect all your digital, all your technical chains or entities in the mining operation. And obviously this will allow you to maximize the value through effective planning, and obviously at the end of the day, if you have that intact, you can now have a more efficient operation, right? And obviously that allows you to improvements to be done across all the different functions of the mining cycle. Because if the mining cycle, or all the different stages of the mining cycle, if they're all connected, if you make an improvement on either one, you can be able to see the improvements, or no improvements at all on the downward processes or the upward processes. So that's one of the main reasons why I would advise most mining companies to sort of like have that platform or a database where the data is all kept in one area and the data can communicate with each other. Imagine having geologists, mining engineers, surveyors working on all these siloed-based systems, and at the end of the month they need to come together and try to make sense and try to make all this data fit. But if you all working on one platform, that eliminates all of it. So all the data is in one, and all the data is connected. So your mining engineers can work on the platform, your geologists can work on the platform, and you don't have to export and import, which can actually affect your data at the end of the day and affect the quality of your ore body or your block model due to different versions of the truth coming into your data, right? So resource evaluation. So raw exploration drill log data will be worked on and turned into something useful, right? And this is just a picture, but you'll see it live later on. This is just a picture of something or a picture of how geologists would take raw data, for example, your drill information, sampling data, and then create all these beautiful pictures from raw data, right? And there's a step-by-step process that gets involved in order for you to be able to create these lovely pictures, and I'll discuss that in detail. So the evaluation process is more like a step-by-step guide on how the pictures are created, and obviously it starts with your geological information, which can be your drill logs, geological mappings, your rock chip samplings, and that has that data then boils down to the steps below, right? We can be able to mix up the steps. We don't have to start from the first to the last one, but some in most instances they follow them exactly as said on the slide. So you collect your geological information, build your 3D model, and then create your block models. So with the geological information, the information that you collect on the field, underground from your drill core that's been locked. All of that data can contribute directly or indirectly in creating the next step, right? Which is your block, which is your geological model. And the geological model depends heavily on the first one, because most of your envelopes or most of your lithologies or your grades would be brought into the system by the first step. And that's how you're able to create your mineralization envelopes. And the envelopes, the mineralization envelopes, they could have like sometimes hard boundaries or soft boundaries. Hard boundaries meaning that the actual envelope itself or the deposit is being cut out by a geological structure, which can be a fault or a dike. And your soft boundaries could be like there's a gradational transition from one lithology to the other, and that could later on be determined, or the hard boundary could later on be determined once mining starts, once mining is, right? And the third step would be creating your 3D block models, which is the most complicated out of all. So it's a process of just using sample data to predict the most the distribution of the grades on the ore body or the geological model in space, right? And in order for so the only thing that we know about the 3D creating a 3D block model is that it'll always be wrong. Okay, so you can never get an accurate 3D block model. And the mere fact that for the fact that we can never we can always be able to, because this is just, we use methods and algorithms to determine what's happening underground without even us getting to underground, right? So basically the 3D block model, we can never know the exact grades on how the grades are distributed underground, and the only time we can actually know how the grade is distributed is that when we actually start mining the ore body. So when the ore body is now getting depleted, that's when we actually get to know the exact grades of the exact grades on how the grades are distributed. And probably that's too late for us. All right. But fortunately, we do have ways or methods that we can sort of like get accurate predictions or get close to being accurate by using geostatistical methods. Mentioned to your inverse distance and your kriging methods. I'm going to spend a bit of time on the inverse distance on the demonstration, and these geostatistical estimations, they can help us to give some reasonable idea of how the grade is distributed in a 3D space underground, and hopefully have a good estimation for us to base our financial calculations and allow a sensible decision to say if it's a good deposit to mine or if it's not a good deposit. So we depend heavily on these algorithms to be able to make decisions at the end. Right? And then once we have all those 3 steps, we can now then be able to determine your resource. Okay, so I'm gonna move out from the presentation now, but I'll come back to it later and jump over to the software. So when Dr. Linda invited me, my worst fear was that I had to present to students, and obviously I have to present like papers, articles, journals, and unfortunately today that won't be the case. I'll just be working on the practical side of mining when it comes to practical side of geology, when it comes to the mining side, where we work a lot with software, and as mentioned, we take a lot of raw data, make sense of the data, so it can be used on the downstream processes, right? And there's actually a step that I've mentioned, the evaluation process. I'm going to try to demonstrate the evaluation process from beginning to end, and how we actually get to paint the picture, and then pass on the picture or pass on the the geological model and 3D models to the next phase, which is giving it over to the mining engineers to be able to make designs and to come up with a mining method to optimally extract the ore body. So first of all, let me just introduce the software. It's called GeoMine. It's a software, 3Dify software, mining software. So it's more like a platform as well. So because most of the tabs here that you see, they are used by all different departments or entities in mining. So you have your geologist working on your geomodeler tab, which includes all the geological tools that you need in order to be able to create wireframes, in order to be able to create meshes that can represent your ore body, or to even create block models or update block models and adjust block models as well. And your ore chaser as well, being one of the modules that mostly used by geologists, that really, if you want to uplift your resources, you want to uplift your ore body, you then use some of these tools just to, which are backed by AI, to determine the exact position where drilling should take place. So it sort of like eliminates the guessing of geology as well. And then all these other tools are mainly used by mining engineers to actually take what you created as geologists and create more stuff with that related to the mining side of things, right? So I'm going to start with the first one, which is collecting your raw data. And the raw data, usually we get it in the form of boreholes, right? So you input in your borehole or your data, and it has, okay, cool. These are your different information that you'll be logging on the field or at your core shed. So usually a geologist, every morning, 2 or 3 times a week, they would go to the core shed and core would come from underground. And as the core comes from underground, they would lock the core. And as they lock the core, all the details is recorded on different sheets. You can report them on Excel, but some other mines, they have like software to actually take note of all the information that's been reported. But most mines just use Excel and then just convert it to a CSV file to be absorbed by software, right? So you firstly start with your collars. And then you map all the required information. Okay. Total length. And then your survey. So all of this information is mapped by a geologist. And some of the information, like your survey, it could be like other companies from outside doing your digital survey, and they will just survey your boreholes, and that's how you also get the information as well. And then you're going to link it to the same, to the files that was recorded. And I think you've already noticed that all these different tabs, they have a common tab, which is your name of your collar, I mean the name of your borehole. And this is the key on how we actually link all that data together in order to create a borehole that you'll see later on. Essay. So with the essay, usually what happens at the mine is that you will take the core, split it in half, take the half to a lab, the other half to a lab, and the other half will stay at the mine. And they will just do analysis on the core to determine what grades or lithology that's found on the core. And then from there, they then return the results, and then the results are married together with the information that you logged earlier. And marrying them together, you'll use the key column that I indicated, which is your borehole color, which is your borehole name. And this is the only essay we have for boreholes. And then you have your ability to custom make your own attributes as well. So once you set it, so you have the option of just pulling the data from your CSV files, or pull it directly from a database if you can link to a database, right? And then you just import it. I'm not going to import it because I've already done it. And this is your final results. So this will be your final results of the data that was logged and the data that was surveyed, and the boreholes, which is your raw data that you're going to start working with. And then from there, you're going to be applying your geological skills to be able to create your ore bodies and block models using all of that data, right? And so it's quite a process as well, but I'm just not gonna focus too much on the detail side of things to get an accurate ore body. I'm just gonna show you the steps on how it's actually done, so you can just understand and know how we actually get to create your ore bodies at the mines. Right? So what I'm gonna do, I'm gonna create sections, and from the sections, I'm just gonna focus on one area of the boreholes. I'm not gonna model the entire boreholes. I'm just gonna focus on a specific area, and to do that, we create sections. So we create sections, and from the sections, just allows you to group all the different boreholes, and not just to look at the entire boreholes, because it could be confusing if you do it. So we group them into specific segments or corridors, and the corridor, you can set the specifications of the corridor. So the corridor, I'm going to set it to be 45 meters. So the 45 meters just represents the distance between the back and the fourth, back and the front of the corridor, and it will be 45 meters. So all the boreholes that falls within that 45 meters in the corridor will then be displayed, and you can see them vertically, and then start mapping your ore bodies and your geological structures. Okay, so spacing, I'm going to make a spacing of 20, and the reason I make 20 is that you have the ability to create a negative and a positive corridor, and as soon as you create one corridor, it will create a negative and a positive. So eventually you end up having about 3 corridors that you can work with. All right. So you can actually create more, but for the demo purposes, I'm just going to focus on 3 for now. And then select an area that you would like to start modeling. So I'm just going to select this one here. And you can see all your corridors. So the 3 different corridors are created. The middle one being the one that you selected, and the top one being your positive, and the one at the bottom being your negative, right? So as you create, all the data is also being created on the side on the screen. And I'm just going to focus on one for now, because focusing on all of them at the same time can be confusing, and you might make a lot of mistakes if you do that. So it's easier for me, obviously as a geologist, to find the best way that works for you. So for me, it's just focusing on one section at a time, and try to map the lithology, the geology that you can observe from the boreholes that was mapped, right? So I'm going to switch to section view. We'll switch to a section view. So from the section, you will be able to see how the grade is distributed along the boreholes, right? So this is the information that was taken to the lab, brought back to the lab, and then joined together with your boreholes. But I know there's a lot of technology that's coming into space in the mining geology space, where they use digital core logging software, where you can just put your core log and then it just logs everything for you. And then it also uses like XRF to get the exact grades along the board. Right, so what I'm going to do now, I'm just going to create your polygons. Just going to create your polygons to try to encapsulate, or to try to close up where you find your high grades. And finding your high grades, I assume that's where the ore body is. That's the area of focus. Right, so I'm going to create a closed polygon, just trying to encapsulate all the high-grade areas, and then close it. So it's unfortunate on this set of data the faults were not picked up. So I'm just going to assume there's faults along the borehole data, and I'll create faults as well. So for now, I'm just focusing on the ore body. Then the second part is creating your faults. So along the borehole, you will find like your fault zones, faults that are logged by the geologist that was observed on the boreholes. And there will be an area where you can see that, okay, this area is a fault on the borehole. And I'm gonna create a polyline. So let's say fault was intersected here and here and here. So that'll be your fault that was observed. And then we then jump over to the next section, which will be your second view. All right. So from the second view, you follow the same process as well. You just circle all the high-grade areas. And to be honest, guys, I'm just rushing through this. Usually, when we work on a project or we work with the client, we actually put a lot of time and detail into this, to modeling your ore body. And obviously, at the end of the day, if you put a lot of time and if you put a lot of effort in modeling the ore body, you will get a close to perfect ore body. So for now, I'm just showing you the process and how it's done, but I'll later show you how the actual ore body looks like. Okay. So I'm gonna do the same here. Create a polyline along where the fault was detected. And then lastly, do the last, and then switch to the last one. Do the same as well, yeah. Then create your fault. Create your fault. So we've done with all the sections. And from all the sections, as we were creating, you could see like the tree was also growing as well. So with every 3D geometry that we create, it's also created on the tree as well. So we'll be able to track it down on what was created, and if you can also be able to switch it on and off in order to focus on specifically what you'll be doing at that specific time. So for now, I'm just going to be switching off all the drill holes because we're done with them. Okay, before, let me just exit the view. So this is the information that we're able to pick up from the boreholes. I'm just going to switch off. Right, so this is all your information that was detected. Let me just try to move out of the view. Right. So the next step now is to separate all your information. So I've locked together your ore body and your geological structures. In this case, will be your faults. So I'm just going to switch some of them off. Okay. So now you have your ore body that was mapped from the borehole information. And then from there, we're just going to join them together to create a wireframe or to create a solid. And that solid will then represent your ore body. Right, so yes. So eventually now you get to now turn the data that was collected from in the field into data that can be used by downstream processes like your mining engineers, and this is your ore body that was created from the boreholes, right? I'm just gonna show you how the actual ore body looks like. All right, so a lot of time and detail was put on the actual ore body. So because I just roughly went through the boreholes and just trying to encapsulate the high areas, it's not that 100% accurate, right? So afterwards, once this happens, you then spend a lot of time again cleaning it up to represent what's actually underground. Okay, and the next step in the evaluation process is then we then move to creating your 3D block model, right? So with the 3D block model, I think this is where the complication or the difficulties when it comes to modeling comes in, because with every company or with every geologist, they have some sort of a preference on the geostatistical method they prefer to use. And as I mentioned, there's multiple. There's inverse distance, there's creaking, there's nearest neighbor, but you'll be able to see that now, right? So the next step now, since we are satisfied with our body, we can then remove it and now bring back the boreholes again. So the boreholes now will be a combination of the boreholes together with the ore body that we created in order to create a block model. Okay, so bring back the boreholes, but then this time we're going to be converting the boreholes into composites. So when you convert the borehole into composites, what you're doing is that you're taking the actual borehole and you're creating equally distanced points along the borehole, and wherever the point lands along the borehole in space, it will take the exact grade of the borehole where it is in space at that specific time. All right, so I've already done that for you. So you can see these are, I don't know if you guys can see, these are individual points along the borehole, and the point where the point lands, it will take the exact grade of that specific spot in the borehole, right? And this is what we use to actually create your block model, taking the boreholes and then converting them to composite, and then using whatever methods of preference to run the algorithm in order to create your blocks, which will eventually become a 3D block model. So what happens now is that we go to your GeoModeler, where we do a bit of interpolation. So with the interpolation, we have different algorithms that we can choose from, right? And as I mentioned, you have your ordinary creating, nearest neighbor, sequential Bayesian simulation, which is mostly used. I think a lot of companies are now starting to look into it, and because that's where you're able to create multiple scenarios of your block model, and which eliminates variances, and it obviously could say it becomes much more closer to being accurate. Right? Like I mentioned, you can never get an accurate 3D block model. But for now, I'm just gonna be focusing on your inverse distance, and from your inverse distance, you are able to select your angles and your ranges. So your angles is how your block model will be oriented in space. But then a lot of companies, they don't like just using one specific angle to determine your whole entire block model, because the ore body is not at a flat angle, right? So it twists and turns, and they want to actually get a block model to twist and turn as the ore body twists and turns under. So what happens now is that we have to now create some sort of an average plane along the ore body, and that average plane is your dynamic endoscopy, which enables you which connects with your block model, and the block model will actually follow the plane as it twists and turns underground, and your block model will twist and turn as that average plane. All right, so before coming here now, we're gonna have to we go back to your data and bring back your ore body, where we then convert or create an average plane along the ore body to be used in order to create your block model, which is your dynamic anisotropic. Right? So I'm just gonna use the original ore body, not the one that I created. So you can see how it twists and turns and doesn't have one specific angle in which it does, right? So you can't use your block model to use one specific angle or stick to that angle, whereas your ore body twists and turns. So you need to use the dip and the strike of the ore body. It needs to be imposed as well on the block model. Okay. So how we do it is that we go to your modeler, and then we create a dynamic anisotropy surface from the mesh, which is your ore body, and just create an average plane along the mesh. So this is your average plane that was created from your actual ore body. You do have the option of cleaning it up a bit. All right, but for now I'm not gonna do that. So you see there's outliers there, and you can see the wireframe has a bit of spikes and all of that. So you do have the option of cleaning it up a bit. You can trim it, you can delete one face at a time to make it much more cleaner, but we won't be doing that for today. And then from there, once that is created, you can now go back to your interpolation, where then now you'll be able to select your dynamic anisotropy. You see, as soon as you select your dynamic anisotropy, your angles, they all of a sudden come blank, because now it's going to use the angles of the dynamic anisotropy to orientate the ore body, the strike and the depth of the ore body according to the layer as well. So it focuses on each triangle, the 3D triangle. So each 3D triangle has a dip and a strike, and the closest block to that triangle would take the strike and dip of that triangle. All right. I'm going to stick to the same ranges. So the ranges are more like the area where your project is located. So I'm just going to stick to the same range. So here you are now able to select the dynamic anisotropy that you created, which is this paper wireframe here. And from there, we bring back your shell or your ore body. And so what's going to happen now is that we have your ore body and your average plane along the ore body, and we've already selected the average plane that will give angles to how the ore body how the blocks must orientate itself, the cells, and now we want the results to be created along the original deposit, right? So we're going to be selecting the original ore body, which is the ore body in white. Selected. And we want the interpolation to happen within the ore body itself and not just in space. So the ore body acts like a boundary on where the blocks must be encapsulated. So then compute. Right, and you have your block model created. Let me just take the rest of the stuff out. So there you go. So now you have your block model. So we used your boreholes to create the ore body, and from the ore body we used obviously using your borehole date information and creating your 3D block model, we use your ore body that was created together with your boreholes. And the ore body just helps you encapsulate your block model, or otherwise it will just be running in space and then forever run without getting any results. Okay. So here's your block model, and this is the information that you can that's then passed on to your mining engineers, and then the mining engineers will then be able to determine how they can optimally extract the ore body, or even determine the method of mining, right? That's the method of mining depends solely on how the ore body and the 3D model is oriented in space. Okay, so we then move on to the next step, which is more on the reserve optimization. So as a geologist, I don't want to say you're done, but this is the data that you create, and this is the data that they'll use upstream along the mining side, right? But then during the mining, the upstream processes or stages, you'll still be involved as a geologist, because now this block model evolves and more data comes in as mining takes place. And as more data comes in, you still need to go back again and update your block model on a regular basis. Usually at the mines, they do it about twice a year, your long-term block model, and then your great block model, which is something that can happen on a monthly or ad hoc basis. Okay. So we then now move to the reserve optimization side. We'll just be looking at how the pit is created using the block models. Okay. So creating the pit, it uses algorithms as well. So the main algorithm is your Lekgenge algorithm, which uses the block model and how the block model is orientated to be able to get the perfect shape of the pit, right? And to get the best cut along the ore body. So because GeoMine is a formula-based software, we usually create formulas to be able to determine if either a block would fall under, would be waste, or would be reef, or would be ore. And we just use formulas for that. And that's how you're 100% sure if you use formulas, no, you won't actually, or there's no block that can slip through the cracks. And every block that within the block model will respect the formula, and no block will go through the cracks. So it's governed by formulas, which formulas for each and every input that's required for you to create a pit, and to create a nested pit. So in this case, we're just going to create one nested pit, and we use your median downscale. Some softwares, they prefer using metal pies in order to get your different pits. But with GeoMine, we use your median downscale percentage, which uses the dollar value of each block scaled down by a percentage that's been given by a user. So in this case, it's 99%. It should never exceed 100%. And if you have, for example, 4 nested pits, the median scale will be like 24.9. And the reason why it shouldn't reach 100% is that you need to be able to give space, or create space, a separation between the different pits that will be created in this case, right? So for now, we perform the pit optimization. Now, before we even do that, there's other parameters that we can adjust. So this is mostly for your rock engineers, where they look at the stability of the pit, or the ore body in the rock. That's where the ore pit will be created, and then obviously determine the best angle to get to the ore body of creating the pit. But as well, you can also have other options of using actual lithology, of the lithology that was detected by boreholes, obviously each and every different ecology has its own strength, and you can use that in order to create the angle of the picture, right? And with optimization as well, because you already know the levels that you're currently focusing on, you don't want to optimize the entire pit. So you have the ability to reduce the level or elevation where you want optimization to begin, and which obviously will make your optimization faster. You'll get quicker results if you do that. And then your sensitivity analysis. With your sensitivity analysis, we do have your variables that cannot be controlled by the mine. For example, you have your gold price. I mean, the mine doesn't really have influence on the gold price. So that's why we have a sensitivity analysis that can sort of like adjust according to the variables or according to the variables that was given. All right. So these are all the different variables, variable values, and this will sort of like keep this in mind that the gold price varies according to the variables that was. Okay, and stochastic analysis. This is mainly for the geologists at the mine. So before this can happen, it has to use your statistic. Let me just get it here. You have to create a block model using your sequential Gaussian simulations that creates multiple block models, right? Just randomly create multiple block models and could create 6 at a time. And those block models, they are sort of like related to each other, but they vary slightly. And that is obviously to eliminate any data that might not have belonged. And obviously, from there, we can use that entire group of block models that was created to create your pit. So by just loading them, and then it will look into the sequential simulations that was done on the block model, and then it will keep that in mind when creating the pit. Okay. Now we have already ran. I've already run it earlier. Sometimes it can take like 10 minutes, and of which I don't have. So I've actually done it before the presentation, and this is the results got. So now this is the results I got. So these the results I got, you can see it selected piece or a section of the ore body, and that's the ore body that will be mined as an open pit. And then later on during mining, they'll then now decide from the open pit, they'll start going under. Okay, and as soon as they start going underground, there's other processes that needs to start to kick in order for them to start modeling the underground process, modeling the underground designs of your mine, and obviously from there, because the ore body has, throughout the years of mining that pit, the ore body has also evolved as well as more information becomes available as mining takes place. Okay. So this is how geologists work on software. Obviously, I've tried to simplify the process, but there's actually more detail into it. But I guess just for understanding, just to show you guys how raw data is taken from the fields, mapping, and it's converted into something that can be useful. Right? So quickly gonna jump back to the. We're gonna jump back to the presentation. So there's other things that the geologists will be responsible for at the mine, and I think I've touched this as well, whereby they would do your planning of your boreholes and where the boreholes must be drilled. But sometimes, when you have a limited budget, it's difficult to exactly get the exact location where you should be drilling. And recently, we having a lot of AI that's assisting with that. And GeoMine has the same tool as well that sort of like assists in doing your info drilling optimization, which can be used to uplift your ore body, and which obviously takes in mind your drilling budget. So you give it specifications. I want to drill this much boreholes, or I have this much budget, and in please drill boreholes. What can I get from my budget or the current budget that I have? And then it will automatically create boreholes to drill specifically at strategic areas where you can be able to uplift your resources without actually wasting a lot of time, right? And then your ore controller, usually what happens with mining, so after blasting, geologists would come to the field and just pinpoint where the ore is. But honestly speaking, that's just thumb sucking. They don't really know what's actually happening when the ore has fallen onto the ground, and they don't really know what's happening underground. So there's actually tools that can assist them with that. So what happens is that with every blast, it creates a blast model, and this is also backed up by AI. So as soon as more data is fed into this tool, it becomes cleverer and cleverer, and it's able to sort of like predict exactly where the ore is after blasting. So once that is done, you create a block model, and the ore is dispersed on the ground, and then from there it will create a schedule on how the trucks should pick up the ore from the ground, and from there you'll be able to know or tell to say if you pick up on the green parts, which is on your red parts, which is your high grade, for example, take those to your high grade stockpile. But then if you start moving on to the yellow, move to the mid grade stockpile, and then the blue is just waste. All right, instead of just taking everything to your high grade stockpile. So this also helps geologists to sort of like make decisions in the field and to avoid a lot of time sucking. Okay, I'm not going to touch the case study. So that is me for today. You can follow ThreeDify on LinkedIn. Thank you.
For presenting this to us, Donald. It's so different, it's so foreign for us academics, but it's very good to have, especially for the students, because this is maybe them next year. Yes. So it's good that you see the language and the kind of software that is used when you're eventually going to work in a mine. Is there any question from the student that you want to ask Donald? Please go ahead.